Well, hello again, everyone, and welcome to this Wind Power Engineering and Development webinar, Asset Management for Maximizing Wind Farm ROI. I'm your host, Paul Dvorak, editor of Wind Power Engineering and Development magazine. Thank you for joining us. Just a little bit before we start, here's an agenda. This webinar will be available on windpowerengineering.com, and a link to it and all the slides will be emailed to everyone, along with 2 white papers that elaborate on related topics. At the end of the presentation, we'll have a brief question and answer session. Now, of course, not everyone that wanted to watch today's webinar could be with us, so you can help them learn from it by tweeting key points and the takeaways that you think important. In your tweets, be sure to include the hashtag WindWebinar. Okay. After the presentation, I'll read the questions that you and the audience have submitted. And you can do that by typing them into the questions box on your GoToMeeting panel that should be to the right of your screen. Now, I'd suggest not waiting to the end of the presentation, but type them in as they come to you, and we'll try to answer as many as possible before the hour is up. Now, let me give you a little background on the topic, and then I'll tell you a little bit about our speakers, and I'll turn the microphone over to them. Now, you know, the wind energy has become one of the best ways to address the constantly growing need for electricity. As a clean power source, it also reduces the need for countries to import their energy. But wind farms are difficult creatures. While the calculated maximum efficiency of a wind farm is only about 59%, few farms really come close to this. Here in the U.S., only 2% of our power is generated by wind, but this will significantly increase over the next 10 to 15 years, with many states mandating that 20% of their power come from clean energy. Now, finally, a concern that we know is close to you and your companies, the time it takes for a wind farm to go from inception to generation. It can range from 24 to 48 months and sometimes longer. Now let me tell you about our speakers, 2 high voltage guys. Our first presenter is Nick Powers. He's the high voltage instrument transformer marketing manager. Nick has been working in the instrument transformer industry since 1978 with experience on specialized transformers with ratings from 600 volts up to 765 kilovolts. Now, since joining ABB Coleman 15 years ago as a business development manager, he has been instrumental in developing advanced designs targeted for independent power, changing market needs, along with helping support other electric utility requirements. Currently, he's involved with several strategic initiatives in renewable energy, rural electrification, and advanced applications for instrument transformers. And our second speaker is Jeff Barker, Business Development Manager of High Voltage with ABB. Jeff has been with the company for 18 years. His background is in control systems and industrial applications, including pulp and paper, chemical, pharmaceutical, metals and mining, and wastewater. Jeff has also spent time in the ABB Power Systems Group in marketing and sales for substation automation solutions, and in the Power Products Group as Business Development Manager for asset monitoring solutions for high voltage breaker applications. Jeff holds a Bachelor of Science in Electrical Engineering Technology from the University of Maine. And with that, let's get things rolling. Nick Powers, the microphone is yours.
Thank you very much, Paul. Here at ABB, we feel it's very important to help developers and turbine OEMs advance wind farm development and solve some of the most difficult problems that you folks are facing on getting return on investment from these facilities. And specifically, when you look at it, we have to focus on 5 key areas to help develop, design, build, and manage the wind farm. Basically, it boils down to these 5. It's delivery, efficiency, reliability, and or maintainability, risk management, and safety are all clearly important to the success of the wind farm. So over the next 30 to 40 minutes, Jeff and I will discuss 2 most important topics, at least most important to Jeff and I, specifically looking at wind farm asset monitoring and asset measurement that has a direct bearing on your bottom line. So it's extremely important to get the message across what's best practices in these 2 areas. So with that, let's first start with Jeff and asset monitoring. Over to you, Jeff.
Thanks, Nick. Today I will discuss diagnostic and monitoring systems for SF6 circuit breakers. The challenge with any type of condition-based monitoring system is the consolidation of information for users to make informed decisions. The intent of such a system is to provide equipment monitoring packages that will assist users to move from time-based to condition-based maintenance. Customers are facing many challenges in a rapidly changing industry due to resources, knowledge base, and even regulations that can be supported and automated with technology. For example, we use the implementation of monitoring in our daily lives. Car tire sensors, service engine light, the strip on the back of your razor blade, just to name a few. So in the case of a maintenance manager, we do a similar concept for many areas of a circuit breaker, such as repairing or topping off SF6 gas, fixing a heater coil before a temperature becomes an issue, even determining the mechanical integrity of the mechanism upon each operation. These are just some of the areas of improved efficiency that users can realize with condition-based maintenance practices. Here, in this particular picture, we are showing how an asset management system can consolidate information into a single user interface, regardless of the many different types of information that may reside in multiple data sources. The primary goal of asset monitoring is to provide a system for continuous monitoring asset health. When a fault is detected, a diagnosis of the root cause of a problem is reported to a user so that the problem is minimized and the user can turn their efforts to immediately resolve the problem. Event-driven reporting means that the assets inform the users that attention is required by providing a consistent monitoring and reporting solution for all assets. A standardized approach to managing information is provided by the asset management system. There are many challenges to implement such a system in an existing fleet of assets. Due to the reductions of resources, we are finding more and more customers looking for providers to support the implementation of solutions. The days of utilities developing their own standalone systems are too costly to implement and maintain. An effective asset system will allow connectivity to many different system types to support the consolidation of information. As we discussed in the previous slide, getting the information to the right person is critical to any successful monitoring solution. Implementing intelligence at the asset level will increase productivity for the end user. Such features as like alarm management, reporting, and even alarm notification for critical issues that arise. As for equipment monitoring packages, they are installed at the asset level, or in this case, the breaker control cabinet in the substation. Due to the old technology of equipment in the substations, communication has now become a greater issue. How can we get the asset information to a centralized asset management system due to the lack of communications at the substation level? Potential concerns with the bandwidth and even the challenges surrounding NERC SIP compliances. Typical breaker monitoring packages that are non-operational data that can be separated from traditional SCADA equipment to eliminate any compliance with NERC SIP. But this does not eliminate all the challenges of the lack of infrastructure. Options such as wireless communications becomes more apparent in the efforts to design the proper architecture. Here you can see a compliant smart grid solution that continually monitors the health of a breaker or breaker types. Support of smart grid initiatives such as these allow customers to justify funds as part of federally sponsored stimulus packages and even PUC rate increases to help support transmission reliability backbone projects. As we mentioned in the slide previously, communications can be a major roadblock. We can offer communications factors that are tied to many different levels, such as the control house or even a central location. We have utilized current technology to implement many different types of communication architectures such as cellular, mesh networks, and even hardwire. We have seen immediate savings with wireless applications for those remote sites, including wind, that provide limited or no communications. This bridges the gap from the device to a centralized local asset server that can provide user workstations centrally at that location or at the substation level, and even dedicated historians. Even the connectivity to other customer systems to existing historians or CMMS systems, central maintenance management systems, also known as work order systems, or data service for documentation such as drawings can all be tied together. Finally, remote accessibility provides a cost-effective means for us to help manage system improvements, provide subject matter experts, and even potential upgrades. Our asset optimization system provides complete integration of devices regardless of manufacturer or type. Features such as asset condition monitoring and reporting ensure fast, reliable, proactive implementation of corrective measures. Intelligence of the cause and recommended actions support the users to increase the time to repair, as well as reduce the number of substation visits to identify the problem or even have the adequate tools and parts required. Alarm reporting features can be utilized to support KPI, the key performance indicators, support of long-term trending features to provide early indication and our previous health aspects of the assets. System integration can offer a means to bridge the gap to documentation such as spare parts, SOP procedures, manuals, and more. Integration of the CMMS systems allow the users to use real-time condition data to optimize the maintenance cycle associated with maintenance or condition-based maintenance. Messaging service, sends messages with alarm information to pre-configured pagers or email accounts or SMS devices. It allows configurable user groups to assign messages to specific individuals or groups thereof, as well as the specific conditions that are deemed critical for the application at hand. And also, finally, remote connectivity will also provide the user the access to AV experts around the world to help reach out and support the efforts associated with condition-based maintenance. AEB's Device Integration Center creates objects and enriches them with all aspects for efficient device management over the entire life cycle, from the design phase to maintenance. These aspects include support for functions such as device configuration, commissioning, diagnostics, operation of device functions, device software, and documentation accessibility. We have field tested and implemented many communication applications within high voltage transmission substations. Even the ability to structure and set up the proper security methods within wireless devices are critical to the end users. Another key element associated with the communication is the validation of data being monitored. Knowing the information being displayed at the asset level is correct. We do this in two separate methods. First, the AEB monitoring devices offer an integrity feature that can indicate any sensor or data issue at the breaker. The second level is done from the asset server to continually poll a device to ensure that proper communications are not lost. Thus, an alarm will be generated and the condition will be suspended indicating a specific area of concern. This is critical, knowing or understanding whether or not that the data that is received from the user is accurate and appropriate. As part of this, AEB has been designing equipment monitoring packages since the mid-1990s. These monitoring packages consist of electronic devices that are built in the U.S. specifically for high voltage breaker applications, primarily SF6 gas breakers rated 69 kV and above. Our monitoring packages range from a standard SF6 gas monitor to a full-featured device that support all of the four areas of monitoring that you see here. Our universal monitors can be used for any SF6 breaker, regardless of manufacturer. Even supplying our monitoring package to other OEM manufacturers to allow the end users the ability to receive monitoring packages on all their factory purchased breakers. In addition, as for retrofit applications, AEB can provide installations on any breaker type. Retrofit projects have been targeted specifically for critical applications such as extra high voltage, cap bank, nuclear, hydro dam, and even remote wind farms. Our devices are installed in the breaker cabinet, as mentioned earlier, and use specific sensors to pull the necessary information into a microprocessor designed to provide advanced mathematical algorithms. So, for example, the interrupter wear algorithm involves the phase currents that provide gradual accumulation of interrupter wear, which will eliminate any non-intrusive inspections. This method provides a life expectancy of the interrupter based on the number of operations, either due to fault or basic switching situations. SF6 gas algorithm, as we all know, the EPA, or U.S. Environmental Protection Agency, has regulated that every customer in the U.S. is required to report the amount of SF6 gas usage on an annual basis. As of today, there are no apparent thresholds for the amount of usage except for California. CARB, California, also known as the California Environmental Protection Agency, Air Resource Board, requires a threshold of percentage that will be reduced 1% on an annual basis, as well as the potential penalties for non-compliance. So our advantage of this algorithm is not only to provide early detection and rate of leak prior to the traditional contact alarms. This will allow adequate time to schedule an outage to not only repair the leak, but reduce the amount of SF6 gas losses. As for the mechanical system, breaker timing parameters can be extracted using dedicated travel sensors or auxiliary switch timing methods. The CBS provides a travel curve to determine reaction time, mechanism time, total travel, and contact velocity. This is calculated every time the breaker operates to continuously capture and trend any mechanical changes. Finally, the electrical controls and auxiliary include peripherals such as heaters, motors, motor run times, core energization, core continuity. to ensure that when the breaker is required to operate, that it will do so without a failure imminent in the design or not in the aspect of that breaker. And finally, AEB remote services, which combine secure remote connectivity with technical capabilities, can include complete and total asset management responsibilities, tailored to the individual needs of a system. And beyond furnishing periodic reports and maintenance recommendations, AEB can automatically dispatch expert service personnel to address any site issues whose needs are remotely detected. Thank you for your attention. Now I'd like to hand the mic over to Nick Powers. Nick?
Thank you very much, Jeff. Now let's get into really what motivates everyone on the line, and that's money. One of the critical aspects, once you've generated the power, is generating the maximum yield for the power and getting paid for it, because that's really what motivates development of wind farm applications, is to get paid for what you do out there. And one of those critical aspects is really how you meter it. And that's the center of what I'm going to be talking about this afternoon, and that is metering accuracy and how to maximize that performance for what is needed in these particular sites for wind farm development. When you look at a typical wind farm metering scheme, you really have two locations you have to consider. You've got the true IPP metering point. That's where the power passes from the generator to the transmission connection point. And that's typically higher voltage application. You also have a owner's metering point back on the 34.5 kV side between the generator and the step-up transformer. And both of these locations have their own purposes and specifically identify efficiencies for both. For instance, on the high voltage side, shown here, 138 kV combination CT-VTs, those actually meter the power flow onto the transmission grid. That's what the owner gets paid from in that particular material. The units on the left-hand, or the center of the picture on the left-hand side of the generator step-up, are 34.5 kV CTs and VTs, and they quite often are typically the owner's way of identifying and tracking efficiency on the farm and generally determine how much power is being generated. So both of those have needs specific to accuracy requirements. But mainly the primary focus is really to get the power out to the transmission and get it billed correctly and accurately to maximize your yield. All right, so let me step forward here on the performance. Let me see here, step down. There we go. All right. One of the first things that we had problems with when we first looked at the development of wind farm was that there was extreme wide current swings in these applications. And the reason why those swings existed is, of course, when you're generating power with a device that's 59.5% efficient, you're not always up and running 100% of the time. So you have varying current levels flowing to the transmission grid depending on the availability of your turbines. And so in this application, currents can adjust wide across the number of operating windmills operating, and it also can operate to the point where you go all the way down to the very low level when nothing is rotating, and the transmission grid operator is actually sending power back into the facility for auxiliary power needs. So those wide swings of current, going back 12, 13 years ago, we didn't, as an industry, we didn't really know how to address the need to meter that location or range accurately. So we really had to look at specialized devices at that time to help address the need. So when you look at the typical 0.3 class transformer, which at that moment in time, 12 years ago, that's all we had tool-wise to take to this application, it had limitations. 0.3% accurate was acceptable for normal metering installations where you stayed within a given rail of current level measurement. And as you see here, a 0.3 class device really starts getting inaccurate as you go lower and lower in the current level. At 100%, you're in the 0.3 class. Down at 10%, you're in the 0.6 at 6% accuracy class potentially. And below that level, nothing is defined. So from a metering perspective, you really want to stay up in the upper regions of that measuring range to be able to get the best accuracy and maximize your return. Unfortunately, this particular model didn't work well on the on the wind farm model, because in this case there was great concern to both the owner and the billing entity that you weren't being covered down at the low end in this region down here in the pink. So something had to be done, and that's when manufacturers started to work about 12 years ago to develop a device that was better, more accurate in its performance. Now why is accuracy important? Let's take a quick view of why accuracy is important here. Let me step down here to the next slide. Here's a quick calculation for a relatively large wind farm being metered on the high voltage side with those 345 kV CTs and VTs in the upper left-hand photograph, tied to the meter down here in the lower left-hand photograph. In this case, you've got 500 kilowatt hours monthly meter reading going into the meter, which is the low voltage side of the instrument transformers. That's not the primary side. But going into the meter, you had 500 kilowatt hours, and at a rate of 3 cents a kilowatt hour, with the meter multiplier transferring it to the primary side of 144,000, you can see a monthly bill of 2.16 million to the transmission grid, and that's a fairly substantial amount of money. And of course, annually speaking, we're looking almost $26 million. So when you look at this application and say, okay, if I can improve accuracy from 0.3 to 0.15, very minor movement in accuracy performance, but in this case, a tremendous amount of return based upon the fact that at that level of billables, you've got a great return potential. So from that point, accuracy we know is important in these applications. Now going forward, when you look at the industry in 12 years ago, we did not have a better class than 0.3. And then all of a sudden, 2005, along came the IEEE C57.13.6 standard. And it says, okay, we're going to define a 0.15 class. Now, I have to tell you, manufacturers were already doing and producing 0.15 classes well before that time. It just wasn't covered under the standard. We were meeting the functional needs of the users out in the industry. So with this introduction of the 0.15 class, IEEE formalized what that meant. And that was an important target because when everybody is using standardized specifications, we all know what the expectations of the other parties are. So in this application, going to a 0.15 meant reducing the error by 1/2 over the 0.3 class. So from 100% of rated current to a rating factor value, shown here as 3.0, that device is in the 0.15 accuracy best range. When you go down and go below 100% down into the 5% of current range, it can degrade down to a 0.3 class, or 1/2 of what the original 0.3 classification was. In other words, it was 0.6 down at that end on the 0.3 class. Here it's 0.3 error on the 0.15 class. So everything is cut in half in terms of the error values. And what's more important, we're starting to see an expansion of that current measuring range all the way down to 5% of rated nominal current. So in this application, this was a move in the right direction, getting into a 0.15 accuracy class from the 0.3. But when you look at the reverse power needs with wind farms, this wasn't adequate enough. And so therefore, it sort of left us lacking a product specific for wind farm or renewable applications. Now, this was valuable in the form that it did provide us a standardized format to sell to other applications. For instance, base load generation facilities don't normally have that reverse current measurement need. And so therefore, by taking the 0.15 class, defining it in a product that's easily applied, like you see in the slip-over CT down around the 138 kV bushing in that little photograph on the upper left, we are able to get 0.15% accuracy from 100% of rated current all the way up to rating factor of values. And then we could take the 0.3 revenue class that had up until then been excellent for revenue metering, take that 0.3 class all the way down to 5%, which was an advancement for the industry at the time. So in this application, we're really able to provide excellent metering performance on all those baseload facilities that during deregulation had to be separated from the transmission grid operator via a metering point. So that was extremely important in locations connecting to PJM or ERCOT out there in terms of the ISO requirements. So Going forward with that configuration, another reason why it was important was some of those products also took a different form to make them easier to install. So in front of this combustion turbine facility, you see 3 slipover CTs in a 0.15 class metering the power flow from that facility onto the transmission grid down in Texas. The advantage here is it's less expensive than a freestanding CT. It's easily installed. It doesn't have infrastructure requirements for a freestanding type device. But the advantage of the CT is we were able to get 0.15% performance, unlimited through fault, because it's just a passive slipover CT, a window type CT provided over a cable terminator or a bushing of a power transformer. The drawback of this, though, still relative to the wind farm developers, is that it's not accurate enough on the low end to be used in those applications. We can't use it for auxiliary reverse power needs. So in this application, even though it's excellent for baseload facilities and metering any current for 20 amps and up, it really doesn't satisfy the needs for the connectivity relative to the transmission grid operator. So they will push back on anything that does not provide accuracy below 5%. Now, given that performance, we have a lot of devices out there that we can bring to bear for different applications in the 0.15 class. In this particular situation, we have class 0.15S defined for high accuracy applications specific to the wide range requirements. So this was the effort on the part of IEEE to say, okay, we're going to try to standardize on a device that meets the performance closer to the wind farm developer, the connected utility to meter this power flow up onto the transmission grid. So they came up with the 0.15S class. And the 0.15S class says that we will maintain 0.15% maximum error from rating factor value, which you see out here is rating factor 400% of the nominal ratio current, all the way down to 5%. That was a good move because it showed a wider range performance, but it still doesn't get us where we need to be for wind farm development. So in a way, IEEE took aim at the renewable market, but didn't quite go far enough, in my opinion. At this point, we have customers regularly speccing performance well below 5% for the reverse power measurement needs. So 0.15S is a good specification, and it meets certain needs, but if you have requirements that drop down into the pink range there below 5%, you really have to tell your suppliers your needs at that level, because if you take just the 0.15S definition, it really doesn't translate to them anything committed down below 5%. So remember that and keep in mind your best performance for the range you require. Now, along came, of course, with our requirements, along came the need to provide products into the 0.15 class. And as you see here, we do have a lot of products out there, all the way from 600 volt, all the way up through 500 kV, even up to 765 kV, that will meet the 0.15 class performance over the wide range. So when you look at the illustration, you can sort of see where we've sort of morphed to relative to the accuracy classes available. The traditional 0.3 class has a big span of pink there. The 0.15 design, which tightened up on the pink region of unknown measurement accuracy, and also gave us better performance in the basic line from 5% all the way up to the rating factor value. Then the 0.15S design, again, 0.15 over the wide range. So that's what we call a wide range design. Some folks call them extended range. But in this case, 0.15 over the entire range, but the commitment stops at 5%. And that's a concern about wind farm development. One of the issues relative to measuring wind farm applications was that we have a better than 0.15 class design, and this actually existed before the IEEE developed their standardized accuracy ratings. So this was developed really listening to users like you and identifying what your needs were and providing a solution to your problems. And that came about 12 years ago when we saw the 0.3 and said, oh, this will not work for this application. What can we do to make this product better? So we focused on that particular task and came up with some rather phenomenal material that we could use to allow this unit to expand its measurement range and maintain accuracy, stability, all the way down, in our case, all the way down to 0.5% of nominal current. So 0.5% of nominal current, as an example, a 500:5 ratio CT with a rating factor of 4, showing all the way out to the right-hand side, going out to 400% of rated current, using a class 20 meter, a 500:5 ratio CT could measure accurately all the way out to 2,000 amps, or 4 times 500. It would also measure in the same 0.15 accuracy all the way down to 2.5 amps on the primary. So as you see, we're giving the owner of the farm the accuracy he needs. We're also giving the connected utility the accuracy that they demand to be able to meter their power flow back into the wind farm application. And even at that point, we're splitting hairs down here below 0.5%. We go down to 0.25% of nominal current in the 0.3 revenue metering class, which is an important distinction because you want to know what the guarantee is as low as you can go. And in this case, 0.25% takes it all the way down to just about the level of detection in the meters. So we're really getting into the point of where the instrument transformers are as accurate or more accurate than the solid-state meters they supply. So it's extremely important that advancements over the last 12 years have really taken as much of a turn as I've seen in 30 years of instrument transformer development. Now, when you look at the better than 0.15 class current transformers stacked up against the other classifications, you can see here that the range is absolutely just nearly complete across the entire measurement performance range. Compared to the others, it really makes the others pale in comparison. So the important point here to take away from this slide is metering accurately currents down to less than 1 amp primary, because that may be what you have in terms of your reverse power. But keep in mind, the reverse power, you have to consider all of the loads connected and make sure that you accommodate whatever's going to be the application current going back in for reverse power, including your losses in the power transformers that has the generator step up. Now, we've been talking primarily about CTs, but one of the things I wanted to mention about the combos, the combination metering units are also being used heavily in wind farm development. In fact, if I would say there is a standard, it is to use the combined CT-VTs in installations to save space, so you save cost on the installation, plus combine it with a high accuracy, wide range performance. And so those have been really popular with developers to save a lot of cash going in terms of your total installed cost. Another development that has been extremely important is that we all know that lead time is critical to wind farm development, and if the quicker the better. And in most cases, lead times on development of wind farms are far shorter than some of the product lead times themselves. So a way that we as a manufacturer have been able to overcome that concern is we've developed an all-purpose, standardized design, multi-ratio unit with the wide range high accuracy incorporated. So out of one unit at 115 kV, one part number for every 115 kV system out there, we have one part number that will be supplied that meters accurately any current from 1 amp to 3,200 amps. Depending on your site system condition, you just take it to the site and reconfigure the ratio requirements specifically for that site. And so this has been very popular because short lead times, anywhere from stock to 12 weeks, has been able to help support the development of the wind farms in a much faster mode. And believe me, when you're facing the incentive credit deadline, that lead time is important. So in this application, by using this wide range device with the 0.15 accuracy commitment over 0.5% to 400%, combining that with multi-taps, it's been a real important tool to be able to meter any installation. And you have one part number for a voltage class. So you don't have to worry about too many items that you have to inventory. So with that, now let's talk a little bit about the voltage transformers. We went from CTs to combined units. Now let's talk about the other side of it, and that's the voltage transformers. We do have voltage measurement devices that we put out there to be able to capture the power requirements by measuring the voltage component. Now, I have to say that voltage transformers provided in the 0.3 class really span a variety of accuracy points. If you look at a typical voltage transformer, we as a manufacturer, we bias that voltage transformer to start in the 0.3 parallelogram or the 0.3 class at the bottom end at zero burden. So if I had zero burden connected to the VT, I would be operating just within the 0.3 accuracy class, and I would be reading high by almost 0.3% high on the voltage reading. As you load that VT up, just like a power transformer with regulation, you're going to start dropping voltage relative to the output. So the more VA I put on it, the more load I put on it, the more it's going to be approaching 1.000 or perfect accuracy. And as I pass through the center region on the burden load, so for instance on Z burden, with the 400 VA burden capability, which is double Z, if I take it to Z, I'm nearly right in the center of the accuracy class. And then as I pass on up into the higher burden connections and put more burden on this device, it becomes slightly under indicating by being less than the expected 115 volts out. So accuracy is controllable in this design. But yes, we do have a 0.15 accuracy class, and we do have some customers who purchase the 0.15 accuracy, but keep in mind, the intent here, of course, is to be equitable. So a 0.15 device is more equitable than a 0.3, and it's more accurate, and it meters power more accurately. But let's look at it from perspective, is the fact that now that tightening that device into the 0.15 parallelogram, I'm actually biasing it with less overbilling on the low VA connections, i.e. solid-state metering connections. It's less overbilling, still within the accuracy class, and is still 0.15, which is better than 0.3. But you have to be concerned about paying more to have less over indication on your metering point. So that's some of the reasons why we don't see as many inductive voltage transformers being purchased in high accuracy as we do current transformers, because they have less of an impact on the overall accuracy performance, because basically accuracy is controllable in inductive VTs. Now, one last point I'd like to make about accuracy is the ability of trying to convert existing installed instrument transformers into certified accuracy devices for metering. There are capability out there today where you can do on-site testing to basically recertify a CT, in many cases relay type CT, for use as a revenue metering CT. So we have a methodology that we bring to bear to be able to provide RCF and phase angle accuracy information based upon fundamental formulas on the CT designs and the VT designs. We provide that capability to test that unit on site without removing them from service, de-energized, mind you, but do not have to take them out of the installation that they're based in. So with this type of configuration, you can actually bring to bear CTs that were never intended to be revenue metering, bring them into the revenue metering application. For instance, we did that when Dominion joined PJM. We went in and recertified their facilities for revenue metering by using this technology. So there are methodology out there today to be able to recertify CTs and VTs for revenue metering. So let's summarize what we've talked about here this afternoon and what's important. First of all, proper accuracy measurement is important. That's what you're creating this wind farm bar is to get a return on investment. It's most important to do that as most accurately as you can. So it should be recommended in the 0.15 accuracy class over a wide range. And remember, don't just specify 0.15s. Specify the range of currents you need to measure. And also remember that when you look at the auxiliary loads, factor in the facility needs as well as the losses in through the generator step-up transformer. And last but certainly not least, have certified test reports on hand traceable to standards. All right, with that, I just wanted to remind everybody that ABB will be at the Offshore Wind Power Show October 9th through the 11th in Virginia Beach, Virginia. So come on by booth number 300 to basically take part in one-on-one discussions with product experts on any specification or concerns you may be facing with your specific product and projects. So now back to you, Paul, for opening the floor for questions.
All right, very good, gentlemen. Thank you. Excellent presentations. There's a lot more to the wind industry than just wind turbines, isn't there? Okay, let's see. Let's wrap up with some questions from the audience. Nick, this first one is for you. Even with the low-end performance shown for some of your better than 0.15S products, are customers still looking for a lower reach for metering auxiliary power needs at some sites?
You betcha. We're seeing specs from time and again asking to go even lower, and we certainly have the capability of looking at performance and measurement at a little lower level, but from a perspective of certification, the concern is to be able to trace that current measurement that low and still confirm that it is accurate to that level. So we can do some additional testing, but here's what they're primarily forgetting in those calculations, Paul, when they ask that question, and that is that they're only looking at their load within the facility. They're not looking at the generator step-up losses of the power transformer. And so I've seen that time and again where they've given us a total and it's a target only for the amount of power needed back in the facility, but they failed to remember to include the power transformer losses that also have to be made up as part of this reverse power flow to the facility.
I see. All right, very good. I just want to remind the audience that you can type your questions into the question box to the right of your screen, and then we'll get to as many as we can. Let's see. Here's one for Jeff. With all the discussions surrounding SF6 gas and the EPA requirements, how does your solution support my needs to report and reduce the amount of SF6 usage?
Yeah, good question. Regarding to the EPA, obviously, is one effort in regards to regulating the amount of usage that's out there in the market. Now, obviously, utilities are taking it to another level and trying to be more green or friendly because of the greenhouse gases that the SF6 provides. So there's two methods, obviously. The system actually provides a leak rate or an early indication of a leak and what the rate of that leak is. And based on the application, we also then determine when that particular breaker will hit the low-level alarm or go into lockout or block situation. So it allows you, based on the traditional contact alarms that are in the station, to really help you get ahead of an actual leak, know where that leak is, and then being able to effectively schedule that outage to be able to repair that leak without having multiple trips due to emergency situations where on weekends and those type of things where you may have a low-level alarm that needs current attention or attention at the particular time. The other aspect of this is the reporting feature that we offer as part of our solution, which then will allow you to look at all the particular assets and how much accumulative in the U.S. standard pounds that you may have in regards to the amount of leaks that took place on that asset, so that you can kind of help regulate the amount of maintenance that you think there's going to be required for that particular asset. So, for example, in California, they have a little bit higher restrictions and regulations regarding the SF6 than the rest of the country in the U.S., but they actually ask you to report individual asset usage and those type of things, and they're being penalized on a specific threshold in regards to overall nameplate capacity as well. So for somebody like the California or the CARB, as I mentioned earlier, this particular solution will be very critical for them to help automate that process, being it's very time-consuming and a lot of manual effort if you're doing like time-based maintenance. So those are the things that we can offer users to automate that process, to improve the efficiencies of proactive measures associated with monitoring and maintaining or reducing the amount of SF6 gas usage.
Excellent, excellent. A couple elementary questions here. Will you make the presentations available to us? The answer is yes to that one. And another one is, will the webinar be uploaded online somewhere? The yes somewhere is windpowerengineering.com. That'll take a day or two. All right, Nick, you did so well in the last question. Here's another one. Okay. In the renewable markets, do you see a lot of high accuracy voltage transformers being specified?
Well, as I said to one part of the presentation there, Paul, in all fairness, you need to try to be as equitable as possible in the revenue metering field, and that's certainly what everyone is doing when they started out with the 0.3 class, moving now to the 0.15. But as I said, there's not as much incentive to provide a 0.15 design when they have to pay the extra 5 or 10% to get the VT converted into high accuracy, when just burdening the device accordingly can improve the performance. So the short answer is not as much, certainly not anywhere near as much as the CT high accuracy is requested, but we do get them from time to time on the voltage transformers.
Mm-hmm. I see. Very good. All right, Nick, and one more for you then. When recertifying CTs on your site,
yes,
can this test conceivably reach extremely low-end current measurements?
Well, nothing to that level right now. When they were doing the baseload facilities, we were primarily testing to confirm the 0.3 accuracy class so that they could use revenue class performance on baseload devices. So in this application, we weren't really driven down to extreme low levels, but there is a level where resolution becomes concerned to maintaining traceability to accuracy standards. So the short answer is I would not normally take the on-site test capability or methodology and try to certify a unit to meet the better than 0.15S design unit capability. So no, we couldn't do the 0.5% of nominal current type test. But certainly 5% up can be tested readily, 5% of rated current and up can be tested readily to confirm 0.15 or 0.3 class performance.
Okay, very good, very good. Gentlemen, we've answered all the questions from the audience.
Could I add one thing too, Paul?
Sure, you can.
Listen, we get our best product ideas from users. So if you saw something in there that didn't strike well with you and said, no, we're doing it this way, certainly feel free to contact me and Jeff if you saw something in his presentation that says, okay, you could be sharper here relative to what we need in the industry. We're desperate for feedback from users out there on what's needed to make your jobs easier and also to improve your return on investment for wind farms. So by all means, contact us. We'd be more than happy to spend some time talking to you one-on-one.
Excellent. All right, once again, this webcast will be available for reviewing at windpowerengineering.com. And one final message, you can follow Wind Power Engineering on Facebook, Twitter, and LinkedIn. This concludes our presentation. I'd like to thank everyone for their attention.
Hey, Paul, there is one more question.
Go ahead. All right. Oh, here it is. Here it is. Yeah, it popped up late. Okay, thank you. Can CT/VTs that support revenue metering be magnetized, reducing accuracy? Does that make sense?
Yeah, it certainly makes a lot of sense. Good question, because we see that all the time. If a transformer is driven into saturation due to levels of fault current, and I'm talking primarily about a current transformer. If a current transformer is driven into levels of saturation by a fault level activity, and it's interrupted at flux maximum current 0, they can leave a magnetizing flux or a bias flux in the steel of these low loss, long memory transformers. And so yes, magnetization of the steel can have a direct impact on revenue metering. So when we first test these transformers, the first thing we do is we demagnetize the core, and then we take the measurement on the transformer. So it's always a good practice when installing the CTs. If someone may have circulated DC current through the core or something like that during during a test or acceptance testing, you want to demagnetize it as one of the last things you do, just to make sure you've got the unit reset back to the original factory value. And certainly it wouldn't hurt as making that part of your ongoing test criteria for outages in the future as well, because these wide-range, high-accuracy CTs are very sensitive to magnetization. And so it's a good question, excellent question out there.
Can I ask an elementary question? How do you demagnetize a core?
You basically have to run it back through the hysteresis loop by forcing voltage across the secondary of the current transformer winding with the primary open circuited. That way what you're doing is you're basically forcing that core to go back up through the hysteresis loop and come all the way back down to 0. So you force it to demag and release that remnant flux in the steel. So it's a fairly straightforward performance relative to just driving a voltage high enough up to go past the knee point of the curve. And for these high accuracy, wide range CTs, they're very small cores. So it doesn't take a tremendous amount of voltage to demag them.
I see. Very good. Okay. Any other questions, ladies and gentlemen? Apparently that's it. This concludes our presentation. I want to thank everyone for their attention. From the staff here at Wind Power Engineering, we wish you a good and productive day.